Okay, so we'll just continue where we left off in the morning. Just to remind you, so we ended the discussion by relating a measurable time-dependent Cp symmetry to the following quantity, which defined as F, which was defined as Q over P times A bar F over AF. Okay. In particular, the time-dependent Cp symmetry in B naught decays to a Cp eigenstate, for example, J psi k short, was sensitive to the imaginary part of this quantity. Okay. So next we need to, so this quantity has two components to it. The Q over P ratio, which is related to the mixing between the BB bar states in the BB bar system, and then the A bar over F, which is a ratio of decay amplitudes of the B bar and the B to the same Cp eigenstate. So let's discuss the possible phases which enter this ratio here. Okay, so this will be a discussion of the phases in decay amplitudes. And so the decay of a B meson to an F final state, as we said, is parameterized by a decay amplitude AF. And if we do a Cp conjugation on this process, we have a decay of a B bar to an F bar final state. This is described by A bar F bar amplitude. Okay, and these two processes are related by Cp conjugation. Now, whenever we have a complex parameter in our Lagrangian which enters our decay amplitude, it will appear complex conjugated after this operation. So whenever we have a complex parameter in our Lagrangian, after Cp, the phase of this complex parameter will change sign. So it will have opposite sign in AF and A bar F bar. Such phases with this property, that they change sign when we do Cp conjugation, are also called Cp odd phases, or more traditionally they are called so-called weak phases. Okay, so these are so-called weak phases. So weak phase, technically it's Cp odd. So it changes sign under Cp conjugation. In the standard model, this is the phase in the CKM matrix, and the processes are made by W exchange. Okay. So in the standard model, due to W exchange, okay, among quarks. There is another kind of phases that can enter decay or scattering amplitudes in general. And these phases appear in presence of on-shell intermediate states. So these are cuts and poles in the scattering sheet. So whenever we have on-shell intermediate states in scattering or decay amplitudes. Those kind of phases can appear even if our Lagrangian is completely real. Okay? Even if L is real. So in particular, they're independent of Cp. Okay? Independent of Cp. Which means that for Cp conjugation, their signs will not change. So they will stay invariant under Cp conjugation. So they will appear with the same sign. In particular, when we study decay amplitudes, they will appear in the same sign in both AF and A bar, F bar. And these are Cp even phases, but again, conventionally or historically, they are called the so-called strong phases. So they're strong phase. And this is because in stellar model processes, these phases appear because of strong rescattering of final state products in decays, for example. So, due to strong rescattering in the stellar model. In both cases, only so the absolute value of these phases are never observable quantities. It's only the relative phases which are observable. So we can measure a relative phase between two amplitudes coming with two different weak phases, two different strong phases, or a difference between a weak and a strong phase. Okay? So, in general, only relative phases between amplitudes are observable. So in particular, our AF decay amplitude can have multiple components which come with different weak and strong phases. So we can expand it in terms of sub-amplitudes which contribute to the amplitude, and they come with a modulus and a phase, and each can come with its, in principle, its own strong phase and a weak phase. So in this case, I've labeled the strong phase of the A1 component of the amplitude with delta 1 and the weak phase with phi 1. And so we can have contribution A2, which comes with a strong and a weak phase, delta 2, phi 2, and so forth. We can have any number of amplitude components. Now we can consider Cp conjugate amplitude, and as I told you, that will be related to the original amplitude by a sign change in weak phases only. Okay? So we can describe it as modulus of A1 times I to the delta 1 minus phi 1 plus modulus of A2 times e to the I delta 2 minus phi 2 and so forth. So here delta I are so-called strong phases So Cp even and phi I are the so-called weak phases. So Cp odd. And then these AI are contributions to the amplitude with different phases. Okay. So let's do such a use this parameterization of decay amplitudes for our specific case of the B naught decay to J psi k short, and try to compute Cp violation in this decay. So B to psi k short. The particularity of this decay is that it's predominantly, to a good approximation, is dominated by a single weak decay amplitude. To a good approximation, just a single weak decay amplitude. Namely, this is mediated by a tree-level decay, B going to Cc bar D. Okay, it's a single W exchange. Sorry, S, not DS. So in this case, and furthermore, J psi k short is a Cp eigenstate. Okay. So now I can describe AF to a good approximation as the modulus of it times the phase, which will contain a strong phase plus the weak phase, while it's Cp conjugate, which will just be A bar F, because F is a Cp eigenstate, will be given by the same modulus times e to the I, the same strong phase, delta F, minus phi F, times the Cp eigenvalue of the J psi k short Cp eigenstate, which is just plus 1. So with this, now I can now write my lambda F for this particular system. So my lambda F is now given by eta F Q over P times e to the minus 2I phi F. Okay. This one, it's eta F is the Cp eigenvalue of the J psi k short Cp eigenstate. It's just plus 1 in this case. Yeah. In this case, F is a Cp eigenstate, so F equals F bar. So basically, F equals eta F times F bar, and in this case, it's eta F is just 1. It could have been minus 1. For example, in the decay B sub S to J psi phi, J psi phi can come in both Cp even and Cp odd states. And there we have both possibilities for eta F. But here is just a single Cp eigenstate. yeah, so in fact I can just write this because f bar equals eta f times f, if you want. Okay. Now we can use the fact which we already used before when we derived the compact expression for the time-dependent Cp symmetry, namely that delta gamma is much smaller than delta m in the B sub D system, which means in turn that the absolute value of gamma 1, 2, when we parameterize the effective Hamiltonian, is much smaller than m1, 2. We can also understand this, if you want, perturbatively, namely gamma 1, 2 is an absorptive amplitude mixing B sub D and B sub D bar, and comes from on-shell intermediate states, and it's actually proportional to G Fermi squared, so it's order G Fermi squared long distance effect. And in the standard model for the B sub D system, this is CKM suppressed compared to the dispersive amplitude. So the dispersive amplitude comes from off-shell intermediate states and is dominated by the intermediate T. So if you have B, D, so D bar, yeah. So I can just write this. No, so the dispersive amplitude is dominated by the TT bar intermediate states, T tops and Ws. Of course, this is never on shell for a B sub D system. And this is proportional to VTB, VTD star squared, this mixing amplitude. While the absorptive contributions, which have intermediate, I should write, yeah, D and B down there. While the absorptive amplitudes come from on-shell intermediate states, which can be, so if I have B, D, D, B, can come from charm and light meson intermediate states. So you have U or C. These amplitudes are proportional to VCB, VCD, or VUB, VUD, and are thus CKM suppressed compared to the dominant dispersive amplitude. Okay, but besides the theoretical arguments, this is also justified experimentally simply because we've measured delta gamma and delta m, and delta gamma experimentally is much smaller than delta m. Okay, so this is clearly the case in this system. Now, if this is true, then if we write out Q over P squared, which is given by, in terms of the entries in the Hamiltonian, in the effective Hamiltonian, are given by M12 star minus I half gamma 12 star over M12 minus I half gamma 12. In this limit, this is given just by e to the 2i psi b. Remember, the psi b is the phase which relates the weak and the mass eigenstates in the B sub D system. Okay, and this is valid down to better than 1%. Okay, so with this approximation, I can now simplify my expression for lambda f, which becomes just eta f times e to the I psi b minus 2 times phi f. And from this, I can also write down the time-dependent Cp symmetry, which becomes just eta f times sinus psi b minus 2 times phi f. Okay? Now, in the standard model, we can express both phi f and psi b in terms of the phase in the CKM matrix. So in the standard model, psi b is just given as the minus argument of M12. And as I showed you above, so the dominant contribution to M12 comes from the intermediate top and W exchange box, and the CKM, the phase, weak phase coming from the CKM elements is the phase of VTB VTD star squared. Okay, so this is just minus the argument of VTB star VTD squared. Or equivalently, I can just slightly rewrite this as the argument of VTB star VTD over VTB VTD star. Okay, the second contribution is the weak decay phase, which you can write as minus 2i phi f. So this is the phase factor of the decay, which you can write as the ratio of the decay amplitude of the b sub d bar decaying to j psi k short over the b sub d to j psi k short decay amplitude. And again, I've told you that these decays are dominated by a single W exchange tree decay amplitudes with a single phase, and the relevant CKM combination is VCB VCS star. So this is equal to minus VCB VCS star times the tree amplitude, modulus of the tree amplitude, plus other contributions which do exist but are again CKM and loop suppressed, over VCB star VCS times the same dominant modulus of the tree amplitude plus additional suppressed components. So this actually describes the decay of the B sub D flavor eigenstate into a SD bar flavor eigenstate, okay, which is not K short, which is a K naught bar. Okay? So what is missing is the phase which relates the flavor eigenstate and the mass eigenstate in the kaon system. And in the kaon system, I told you yesterday, I think, or yeah, already yesterday, and today in the morning again, that the amount of Cp violation in the kaon mixing system is very small. Epsilon k is of the order 1 per mil. So in practice, the kaon mass eigenstates are approximately Cp eigenstates, okay, up to corrections of order 10 to the minus 3. So the mixing amplitude in the kaon system is actually up to per mil level correction described by the phase, the same phase, that an analogous phase that we had in the B system relating the B Flavour eigenstates with the mass eigenstates. The same analogous phase enters in the kaon system, okay, and just enters when we go from the Flavour kaon eigenstate to a mass eigenstate of the kaon, the K short. So this is coming from K bar oscillation. Or mixing. Such that the mass eigenstate formed is the K short. Now, this similar to the B sub D system, this phase is also dominated by a single box exchange diagram, except that instead of the top quarks, here the dominant contribution comes from the exchange of charm quarks. Okay? So in this case, we have again the dominant contribution relating KK bar, mixing KK bar states is coming from intermediate charm quarks. So we can read off the CKM factors, which will be VCS, VCD star squared. Okay, so we can write this down. And it becomes VCB, VCS star over VCS. And then the kaon mixing contribution, which will be VCD star VCS over VCD VCS star. In this ratio, the VCS and VCS star cancels. So I can now write the final expression for lambda psi k short. So lambda of a B decaying to a final state psi k short will be given by VTB star VTD over VTB VTD star times VCS VCD star over VCB VCD star over VCB star VCD. Now you can check that this particular ratio you can express it either in terms of the Wolfenstein parameterization or directly in terms of the unitarity triangle angles, comes out precisely minus e to the minus 2I beta, where beta is the beta angle in the unitarity triangle in 3-1 generation plane. Okay. Oops. So we can now plug this result back into our expression for the time-dependent Cp symmetry in this decay B to J psi k short, and we obtain that S psi k short or B psi k short is given precisely by this the sign of this, so sine 2 beta. And this expression holds up to order 1%. okay, due to the approximations that we made in deriving this. Now you've noticed that what happens here is that the Cp symmetry, or the Cp violating observable, or the Cp phase, is actually a phase between the phase in the mixing amplitude, which is this first part. This is basically a phase of the mixing amplitude. And the second part is the phase of the decay amplitude. So it's the interference between mixing and decay. Okay? So that's why we also call this such observables which have this feature as signaling Cp violation in interference. In interference between mixing and decay amplitudes. Mixing and decay amplitudes. Okay, so following this exercise in the B sub D system, we can repeat it almost directly for the B sub S system with a couple of complications. So we can next discuss Cp violation in the B sub S system. Here, the so-called golden channel for observing this Cp violation in interference between mixing and decay is the decay of B sub S to psi phi. And the first complication is that this is a system of two spin-1 particles. So in principle, they can be in different Cp eigenstates, depending on the orientation of their polarizations. So this is an admixture of Cp eigenstates because we have two vectors in the final state. But luckily, using angular analysis, we can actually disentangle these Cp eigenstates, okay? Because they will, of course, come in different angular distributions. So the first experimental or technical difficulty is that one needs to perform an angular analysis of the final state to project out the two different Cp eigenstates. So one needs angular analysis. The second complication has to do with the frequency of oscillations. Namely, so someone in the break, I think, someone asked me about what are the time scales of these processes. So in particular, in the B system, the lifetime of all lowest lying B states are approximately 1.5 picoseconds, while the frequency of B sub D oscillations, which is given by the mass difference of the system, is roughly 1/3 of that. So it's like 0.5 picoseconds. So they oscillate 3 times as fast as they decay, meaning that in a typical lifetime, you will see a couple of oscillations, okay, of these states in their rest frame. Okay. We can compare this to the B sub S system. In particular, we can easily estimate the ratio of oscillation frequencies of B sub D and B sub S, namely this ratio delta ms over delta md, which will be proportional to the ratio of the absolute values of M12S over M12D, so the absorptive mixing amplitudes, dispersive mixing amplitudes. And since they're both dominated by top quark exchange, one just needs to change the D indices in the CKM elements to S, and this becomes proportional to VTS over VTD absolute squared, which is roughly 1 over lambda squared, and turns out numerically to be around 30. Okay? So B sub S mesons oscillate 30 times faster than B sub D, having the same, roughly the same lifetime. Okay? Which means that even, so for example, at the B factories, so the B factory is Bell and Babar, and currently the currently starting super B factory, Bell 2 in Japan. So they produce these BB bar pairs and B sub S bar pairs in E plus, E minus collisions, which are tuned in a way that the E plus E minus scatter on one of the bothomonium resonances which decay to BB bar or B sub S bar pairs. In particular, the upsilon 4S for BB bar and upsilon 5S for B sub S bar. Okay? But this means that the final state, so the B and B sub S mesons, which they travel through the detector and then decay, are not very relativistic, and so they don't experience significant time dilatation. Okay, so the resolution really has to be picosecond resolution, and in particular, the measurement of the B sub S oscillation frequency is much more challenging than B sub D. Okay, because one cannot resolve so finely the time differences. Now, this is different in LHCb. So LHCb is a forward detector, one-sided forward detector at the LHC. So the B mesons, or all B hadrons, are produced as products of fragmentation coming from proton collisions at very high energy. Okay, so typically B mesons at LHCb will be highly boosted, so they will experience significant time dilatation. And this allows for a precise measurement of S oscillation frequency, much more than at the B factories, okay? In addition to having larger statistics. Okay, so this is the second complication. Okay, and then there is the third effect that one cannot no longer neglect in the B sub S system, which is that experimentally delta gamma S is not much smaller than delta M. So when one describes the time evolution of the B sub S bar system, one can no longer neglect these delta gamma suppressed terms. So delta gamma S effects cannot be neglected. Cannot be neglected compared to the MS in the time evolution. Okay, but nevertheless, we can still extract lambda B sub S to J psi phi, and in particular, in the standard model, this quantity can now be expressed as in a very analogous way to the B sub D system, namely minus e to the I psi B sub S minus 2 times the weak phase of the decay amplitude to the psi phi, which then leads to the observation that S psi phi of B sub S, so this is the Cp evaluating time-dependent asymmetry, is given by 2 times the phase of VTB star VTS over VCB star VCS, which numerically comes out in the standard model to be 0.0376. Okay, so one has to compare this with the S B sub D to J psi k short, which is 0.6, so order 1. The phase in, or the Cp symmetry, the corresponding Cp symmetry in the B sub S system is tiny, is of the order of a few percent. So it's much more challenging to measure. And so the current most precise measurements are starting to reach this precision, in fact. And so the measured, this is the standard model value, while the measured experimentally is at the moment at the level of 0.02 with an error of 3. Okay, so we are not there yet to actually establish experimentally this phase, but what we can conclude is that it cannot be much larger than what is expected in the standard model. Cannot be orders of magnitude larger. Has to be of the same order of magnitude. Okay, so this was Cp evaluation coming from observables which measures evaluation interference between mixing and decay. Now, what would be interesting is to also have observables which study purely Cp evaluation in mixing and purely Cp evaluation in decays, and this is in fact possible. And let's discuss both possibilities in turn. And firstly, let us discuss Cp evaluation in B decays to Cp conjugate states, because there one can actually have sensitivity to Cp evaluation in mixing. So this will be Cp evaluation B decays to Cp conjugate states. And these particular decays are interesting when the amplitudes, for example, we have, as you remember, we had A sub f, A bar sub f, A sub f bar, and A bar sub f bar. And these decays are interesting when one of the two channels is forbidden for each of the Cp conjugate B states. So for example, when only AF and A bar F bar are allowed, but AF bar and A bar F are forbidden. So this is interesting. If B naught, for example, to F bar and B naught bar to F are for some reason forbidden. Because then what will happen is that in this case AF will be exactly equal to A bar F bar, of course, but more importantly AF bar and A bar F will vanish. So our expressions simplify a lot. In particular, in this case, when half of these amplitudes vanish exactly, one can then write this time-dependent Cp symmetry that we wrote out before. So it will be the d gamma over dt for b naught bar 0 to f of t minus d gamma over dt of b naught to f bar of t, yes, over d gamma over dt of b naught bar at 0 to f of t plus d gamma over dt of b naught at 0 to f bar of t. So I can construct the following, except that this asymmetry turns out to be time independent. So if we plug in the expressions for these time-dependent decay rates, in the limit of vanishing of these two decay amplitudes, it turns out that this is exactly q over p squared minus q over p, sorry, p over q squared minus q over p squared over p over q squared plus q over p absolute squared. So remember, in the B sub D system in particular, we had that, so P over Q is given by gamma 12 and M12, so the absorptive and the dispersive parts of the mixing Hamiltonian. And in the B sub D system, we had gamma 12 absolute value being much smaller than the absolute value of M12. And in this limit, this further simplifies, and is just given, so we can now expand in gamma 12 over M12, absolute values. And this thing turns out to be proportional or approximately equal to imaginary part of gamma 12 over M12. So what it does, this asymmetry actually measures the relative phase between the absorptive and the dispersive mixing amplitudes. Okay? So again, it's a phase difference between two different amplitudes contributing to the same process. Just now, those two amplitudes are the mixing amplitudes, which can come with different phases. Okay? So this is up to order gamma 12 over M12 absolute value squared corrections. Okay. So again, since gamma 12 over M12 is roughly 0.1 in the B sub D system, this is correct to better than 10% numerically. So as I told you, this is since Q over P are time independent, this is a time independent measurement. So one no longer needs to resolve the oscillations or the time evolution of the state to measure this. So it's a time independent measurement. And it measures Cp violation in mixing. Cp violation in mixing. Sometimes this will also be referred in the literature as indirect Cp violation. Indirect Cp violation. So there is one very good example of this, which is being probed experimentally. And these are the semi-leptonic Cp symmetries in B decays, which are defined as ASL. Of course, they are measured both in B sub D and B sub S decays. So here I put a superscript D to denote that this is a semi-leptonic Cp symmetry of this system. And they can be defined as the difference of the decay rates of a B0 bar to a Cp conjugate, a state which is basically has a charge. Okay, so it has a well-defined Cp conjugate state, and the simplest thing is to actually use semi-leptonic decays, where we can tag the charge of the lepton. Okay, so to be inclusive semi-leptonic decay, where to a positive charge lepton, electron or muon, and a neutrino. Okay, minus the rate of B naught decaying to X L minus nu over their sum. B naught bar going to X L plus nu plus gamma of B naught going to X L minus nu, where the B naught and B naught bar refer to the flavor eigenstate at production. Okay, so at 0 time. So one can compute this asymmetry in the standard model. Okay, and again, it's given basically as the phase difference between the CKM elements in the top W loop and the CKM elements in the charm W loop. Okay, and I will just write the numerical value in the standard model. So ADSL is given by 3.3 with an error of 7 times 10 to the minus 3. Okay, so again, it's a per mil level effect. Okay. And the in this case, the experiments have not yet reached the precision required to measure this quantity. And also, in this case, the semi-leptonic Cp symmetries of B sub D and B sub S are comparable. So they're both at the level of 10 to the minus 3. Okay, so this is a way to measure Cp evaluation mixing, and we have a third way to measure Cp evaluation in Flavour, and this is using purely weak phase differences in decays. In particular, what we can probe for is Cp evaluation in charged B decays. In charged B decays. So these are interesting because, of course, charged Bs cannot oscillate. So oscillations cannot contribute to these to Cp evaluation in these observables or processes, and they're particularly interesting for decays of charge Bs, so B plus minus, going to D and neutral D and the K plus minus, final state. Now here, of course, this is a neutral D, and so the charm meson, neutral charm mesons will oscillate. But we also know from experiment that Cp evaluation, and also from theory arguments, that Cp evaluation in charm mixing is also very small. It's probably even smaller than in kaons and in the B system. So the Cp evaluation in the mixing will not contribute to a, again, better than a per mil level precision. And here the presence of D oscillations will just allow us to have contributions from two different decay amplitudes of the B, because we'll be able to probe both D0 and D0 bar contributions in the final state. So since DD bar oscillations allow for interference of two, in particular it turns out to be one can actually find two competing tree-level weak amplitudes contributing to this decay. Two tree-level dominated decay amplitudes. To the same final state. In particular, one can write down, so a decay of, for example, B minus going to D naught K minus. Now, the decay amplitude to this, for this process is described at the quark level as the decay of a B quark into a C U bar S final state. On the other hand, the same state, B minus, can also decay to D0 bar, K minus. At the quark level, this decay is described by decay of a B quark into a C bar U S final state. Okay? And since D and D0 oscillate, we can find common final states. And we'll have competing contributions from these two decay amplitudes, which will, in principle, have different weak phase, as it will turn out. To simplify our discussion, we're limited to particular final states where the D naught final state contains a Cp eigenstate. Okay. This can be generalized, but here, for simplicity, we'll just constrain ourselves to this particular final states. So this is going to be particularly transparent for Cp eigenstates of D decays. So I will consider D naught decaying to a Cp eigenstate. For example, C going to DD bar U or SS bar U, and D naught going to the same Cp eigenstate, which will be described as C bar going to DD bar U bar or SS bar U bar. Let's try to compute the ratios of these decay amplitudes in the standard model. So what we're looking for is a ratio of a decay amplitude of a B, okay, to a final state with D decaying to a final state F and a kaon over the decay amplitude of a B decaying to a final state d bar, and again, that decaying to a Cp eigenstate f and a Km. So let's write out CKM factors which enter. So the upper one will be proportional to VCB star VUS times the decay amplitude modulus, ADK, times, so this contains the weak phase, there can also be a strong phase, so there will be e to the I delta dk strong phase, but I'm computing a ratio, so I'll also have the other decay mode, which corresponds to this quark level process, which has a weak, the CKM factor VUB star VCS times generally a different decay amplitude modulus, A d bar K, okay, and different strong phase as well, so I can have here minus delta d bar K. Okay, and then I need to furthermore describe, so the decay ratio of decay amplitudes of d to f and d bar to f, so there is another factor which will be given by the Cp parity of the final state f. Okay, since I'm decaying to the Cp eigenstate, can have either positive or negative Cp parity. So again, I have this eta f factor. And then the decay of d to f, for example, in this case, will be described by the CKM factor will be VCD VUD star times the decay amplitude modulus of d decaying to f. So d decaying to f, exactly, times a possible strong phase again. So I delta df over the CKM factor for a d bar decay to f, for example, this one entering this particular decay amplitude, which will be given by VCD star VUD times the amplitude modulus, which will be now AD bar F, again, in general can be different, and in general a different strong phase given by delta D bar. So now, however, I can simplify this a lot by grouping together factors which are real and factors which contain phases, Cp even and Cp odd phases. So what I can write, so I can write this ratio of decay amplitudes in a much more compact way. So this AB to D to F K over AB to D bar to F K can be written approximately. So this is assuming a single decay amplitude dominates completely all this sequence of decays, which is, for these particular decays that I've chosen, holds to a very good precision. Again, So this is up to very suppressed high-order loop corrections. But in this limit, up to these corrections, which turn out to be extremely small in practice, I get eta f prefactor. Then I get an unknown ratio of decay modulus, decay amplitude moduli, which I can just bundle together in an unknown constant RB. And a phase difference between an overall strong phase difference and an overall weak phase difference, which I already note as gamma, because if you compute the weak phase difference, the weak phase which come out of this ratio of CKM elements, it turns out to be exactly this, exactly the gamma angle in the CKM unitarity triangle that I've drawn previously. So this is exactly the argument or the phase of the ratio minus VUD VUB star over VCD VCB star. Okay, and also remember from when I showed you the global CKM fit, this angle is sizable and is around, experimentally is around 70%. Okay, so this is a large angle, so it's a large phase. Now, of course, in this expression we have three unknowns. Okay, so with a single measurement, of course, we cannot determine all three unknowns. Luckily, in practice, we have more measurements which you can perform, which all depend on these same parameters. So we have several decay rates which we measure. So decay rates are only sensitive to amplitude square, absolute amplitude squares. But we can write down the amplitudes for the different decay modes related by Cp conjugation to each other. In particular, the decay amplitude for B minus going to some Cp even eigenstate F plus. So the plus here refers that this is a Cp even eigenstate. And a K minus, I can write it as an overall amplitude modulus. So I have two amplitudes which contribute, ABD to FK and also ABD bar F to FK. So I project out the contribution 1, and then the second contribution of the other is then given by just this ratio. Okay? Since I've chosen the F plus, eta F is 1. Okay, that's why this plus refers to the sign of eta F. I have a plus here. Times e to the I delta B minus gamma. Okay? This would be the full decay amplitude for one of the possible decays. But I can also study three other related decays. For example, the B minus going to the Cp odd final state with the same flavor structure, K minus, will have very similar decay amplitude, except that I have here 1 minus RB, e to the I delta B minus gamma. And then, of course, I can also look at the Cp conjugate processes to these two. So I have two more decays which I can in principle measure. In particular, I can write down the amplitude for a B plus decaying to F plus K plus, and this will be described by A naught times 1 plus RB times e to the I delta B plus gamma. So the strong phase doesn't change sign under Cp conjugation, the weak phase changes sign, so I have plus gamma here. And finally, I have also the decay mode B plus going to F minus K plus, which is given by A naught times 1 minus RB times e to the I delta B plus gamma. So by measuring 4 decay rates, I can extract all the 4 parameters that enter the description of these decay amplitudes: A naught, RB, delta B, and gamma. Okay? Without any theoretical knowledge on the hadronic physics that underlies these decays and possible stronger scatterings or whatever. And so, in addition, since I'm just measuring decay rates of charged mesons, there are no B oscillations involved. So what I'm really measuring is the phase difference of phases of different decay amplitudes. So this is also called measuring of Cp evaluation in decays, Cp evaluation in decay. Or sometimes you will also read about direct Cp evaluation, in contrast to indirect Cp evaluation, which is Cp evaluation in oscillations, in mixing. So, direct CPV. So there are just a couple of comments that I want to make before going to the next topic, or introducing the next topic at least. And that is that, so here, as I already said, using only rate measurements, so in particular decay rate measurements, so no asymmetries, one can extract the 3 hadronic parameters so these are A naught RB, so basically the moduli of the 2 competing decay amplitudes and the relative strong phase delta B, and also the weak phase gamma. In addition, this kind of extraction of the CKM Cp evaluating phase is extremely theoretically clean. It's actually the cleanest way to extract the weak phase of the CKM. So this is theoretically extremely clean. And in particular, this is because Cp evaluation in DD bar mixing, which could, in principle, introduce dependence on an additional weak phase. So then one could compute the weak phase coming from the interference of the DD bar oscillations and B decay, is very small. It is also known to be very small experimentally, but in particular in the standard model, it's extremely small. Below a per mil. Of course, to be able to practically perform this extraction, it is preferable that RB is not too small. Okay, so one looks for decays where the two competing amplitudes have approximately the same, or it never happens that they're the same, but there is not a large hierarchy between the two competing true level amplitudes, such that one can actually extract, because the extraction of delta B and gamma relies on the possibility to actually be sensitive to the RB suppressed contributions to these decays. And as I told you before, I did this for CP eigenstates F of D decays, but one can also generalize this procedure for other D decay final states, and it carries over with a bit of complications. Okay, so let me use the last 10 minutes to introduce finally the next topic, which will be how now, so we've discussed how one can extract the flavor parameters of the standard model, and in particular how one can over-constrain the Cp violation in the standard model to make sure that the dominant source of Cp violation in the flavor sector comes from the CK. Now the next task, of course, is to use this knowledge to try to constrain possible additional sources of flavor violation and in particular Cp violation in addition to the standard model. So let me put it here. So what can these flavor measurements tell us about the possible beyond standard model sources of flavor and Cp violation? So flavor and new physics. So the question that we want to answer is how much, given the precision of the flavor measurements, how much can new physics still contribute to flavor observables, and what kind of constraints this puts on possible new physics. So the question is, how much can new physics contribute to flavor observables? So the first thing that we can check is that from experiments we seem to, the first message is that at least in tree-level dominated observables, so observables where the standard model contributes at the leading order in the weak expansion, so at the tree level through tree-level W exchange, these are very well described by the CKM. And one way to test this is again using CKM unitarity relations, this time not on the off-diagonal entries, which describe triangles in the complex plane, but on the diagonal. Okay? So there is good agreement of standard model tree level dominated processes. There might be some exceptions where disagreement is not as good as we would like. If I will have enough time on Friday, I will briefly discuss those cases. But one good example which demonstrates the level of precision to which this agreement holds is, again, to use CKM unitarity for the diagonal entries. In particular, this holds for the first and the second product row column products. So I can write this, the following CKM unitarity relation, VUD absolute squared plus VUS absolute squared plus VUB absolute squared minus 1. So in this, if CKM is unitary, or if standard model processes give the only contribution to observables from which we extract VUD, VUS, and VUB, then this should be exactly 0. Okay? So how do we extract the moduli of these CKM matrix elements? Oh, maybe let me write it up there. Okay. So in particular, the modulus of VUD is extracted from allowed beta decay. So this is extracted from nuclear beta decays, okay? And is known to, I don't have it, yeah. So these are so-called super allowed beta decays. And they allow for the extraction of VUD, which has the value 0.97 to 5 with an error of 22. Yeah, this is better than a per mil. Okay. Next is VUS. We can extract VUS from semi-leptonic kaon decays. In particular, the decay rate of K plus to pi plus in U would be proportional to VUS absolute squared. Yeah? Oh, these are basically nuclear. Okay, nuclei, yeah. So it's nuclear physics. They're not mesons. You look at oxygen or whatever. No, nuclei. I don't know which is I have to check which particular decay is the one where this is most precisely measured. Essentially, it's neutron decay. Okay, but in a nucleus. Okay, so this allows for extraction of VUS modulus, and the current value is 0.2237 with an error of 13. Okay. Again, this is an extraction of better than 1% relative uncertainty. And finally, we have the measurement of VUB. This can be measured, as I already shown you in the morning, from the rates of semi-leptonic B decays, Habibo-suppressed semi-leptonic B decays. So B decays to final states which do not contain charm quarks. So this is any final state which has the flavor numbers of U and not charm. Examples of these are B2 pi LNU or B2 rho LNU and so forth. And they allow for the extraction of VUB modulus, and the current value is roughly 4.2 with an error of 5 times 10 to the minus 3. Yeah, you're right, of course. Thank you. Yeah. So in practice, however, this value is so small that actually the uncertainty on VUS dominates this unitarity sum. And if you evaluate, so you add up these numbers explicitly, you get that this unitarity sum is respected down to 0.0008 with an uncertainty of 7, roughly. Okay, so CK unitarity relations in these tree-level dominated decay rates, extracted from these tree-level dominated decay rates, are respected to better than a per mil level. In particular, this also allows for another interesting test, which is universality of weak interactions between quarks and leptons. So remember, in the standard model, if we sum up these decay rates, since by definition CKM is unitary in the standard model, by construction, their sum becomes proportional to the Fermi constant. Okay? So by measuring these, by combining the measurements of these decays, we can compare the extraction of the Fermi constant and compare it to the value extracted from the muon lifetime. So this allows for testing of charged weak current universality. Universality between purely leptonic processes like muon decay and these semi-leptonic processes. And semi-leptonic processes. So this is the muon lifetime in particular. Muon lifetime. And the precision to which we can test this is given again by this precision. So we can test this to better than a per mil at the moment. Better than a per mil. So in the following, namely tomorrow, we'll be considering, we'll not be considering new physics to tree-level processes, because that seems to be very suppressed or absent to a good degree. And we'll focus on new physics contributing only to loop-suppressed processes, so the processes which are in the standard model loop-suppressed. And then on Friday, if we will have time, I'll revisit the issue of possible new physics effects in tree-level dominated processes, okay, in some particular cases. So we will consider new physics to suppress processes, in particular to loop and CKM suppressed observables. Okay, and let me stop here, since I'm roughly used my break time. Are there any questions regarding this afternoon material? No? Okay. Then thank you.